We'll wait a couple of more minutes, see if we get a few more people showing up. How are you doing, Ed?
Hey, Luke, how's it going today?
Doing pretty good.
Luke, where are you? Are you based in Austin?
Yeah, I'm in Cedar Park.
Yeah, I'm in Austin as well. Up near the Avery Ranch area.
Mm-hmm. Yeah, I'm not too far away from that. I'm just up Lakeline at Buttercup Creek. So.
Oh yeah, know where that's at. You guys survive the snow vid?
Yeah, we're all still here.
I'm hearing that we might get another bad winter storm this year.
Well, hopefully someone put a blanket around the water pipes.
Making sure my my wood pile's up to snuff.
There you go.
Do you know who the Dell Technologies? Is that Janet or?
Hey Ed, it's Tori Pyle here, helping you guys out.
Hiding behind that Dell Technology, Tori.
I am. I'm very incognito today.
So Tori, you just let me know when you want me to go ahead and get started. And
Feel free to go ahead and start now, Luke.
Private showing.
So. Yes. If anybody joins in the chat, I will let you know.
All right, so we're going to spend about 15 minutes talking about how we can run AI, HPC, and data analytics all on the same systems with greater flexibility using Omnia. My name is Luke Wilson. I'm a distinguished engineer for high performance computing and artificial intelligence at Dell Technologies. I'm the Omnia chief architect. And so Omnia itself is a new method for deploying high performance computing systems for artificial intelligence, simulation modeling, and data analytics workloads. And we have a lot of great tools that we've been using for a long time, but we think it's time for a new approach because the next generation of HPC and research compute platforms is going to be very different from what we have today. Instead of building very homogeneous systems where every single server building block is identical, everything has the exact same compute characteristics, we're going to be building a lot more heterogeneous architectures where we have islands of dense compute and then some GPU acceleration from one or multiple vendors, FPGA acceleration from one or more vendors, and then a whole host of different special purpose deep learning accelerators for both training and inference are on the horizon. We're seeing just within Dell, we're tracking over 40 different startups that have different training or inference accelerators for deep learning or machine learning. And so this whole proliferation, this Cambrian explosion of compute capabilities is making it more difficult for us to develop systems deployment software that can work in a very automated fashion, because the way we're used to doing things now is through the concept of the golden image, where we pack together the user level software, the drivers for the different hardware components, and all the libraries and frameworks, along with the operating system when we deploy it as a single image at provision time. But as we get to much more heterogeneous designs and cluster deployments, this approach becomes intractable. We end up with an explosion in the number of images that we need. We have all sorts of different caveats and capabilities that have to be integrated in certain ways. And so we have to rethink the way we deploy HPC systems in order to more seamlessly and simply get all of the technology that's needed in terms of the software for the particular hardware we're running on. We also want to rethink the way we're doing software deployment at the user level on these systems. We've very traditionally in the HPC space, and I'll talk about this a little later, used a very OS dependent software deployment mechanism where we build software directly on the system for the system that's being used on. And this leads to a massive proliferation in the amount of software development and deployment effort that's required. Many HPC sites have, tens of research scientists with PhDs that spend their entire days compiling software in order to provide them for their user community. And we think that more modern software packaging practices, such as containers, provide a better way for us to distribute software from the point of origin, the developer of the software or the vendor who is recreating a software package with a hardware accelerated component to the user. And because of changes in the Linux kernel, changes in the way we handle containers inside of the Linux kernel, we can actually get bare metal performance from containers in a way that we couldn't before. These are no longer what we used to call lightweight virtual machines. These are actual OS layer run applications where the container is really just a namespace and a C group running within the kernel. And so this gives us the ability to get that maximum performance to rapidly deploy the latest applications without having the HPC systems administration teams at different sites rebuild this software every time a new version comes out. And we can now take advantage of various accelerators and network interfaces from directly within the container. This allows us to really start branching out from the traditional simulation and modeling space to start looking at more emerging workloads, such as distributed and accelerated data analytics, machine learning and deep learning training and inference, and a whole host of other types of applications that are outside sort of traditional materials, thermal, computational fluid dynamics space that has been the traditional simulation and modeling area for 20 or 30 years. And we want to take lessons that have been learned in the enterprise and cloud service provider space and bring them to the HPC community. There's an entire ecosystem of tools that have been developed in the last decade to help automate very large scale data centers at the enterprise and cloud service providers level that didn't exist when most HPC deployment tools were created. And so we want to take advantage of those automation tools. We want to take advantage of those capabilities. And we want to start thinking about HPC systems in the way that we think about cloud resources or resources in an enterprise data center, where they can be reused for different purposes at any given time. They're not part of a fixed infrastructure. They're tailored to the needs of the user, to the needs of the research group. And when you're done using them, you can just easily tear that infrastructure down and reuse it for other purposes. And so because of all this, we decided it was time for something different. We actually started this as an internal project just within the HPC and AI Innovation Lab at Dell, just to put up POC systems in the lab because we stand up and tear down clusters on a very regular basis. They only live for about 4 to 6 weeks. But we realized very quickly that this is something we thought the community as a whole would be able to take better advantage of, the community would be interested in. And so we started the Omnia project as really an open source community-driven framework for composing high-performance clusters. Now I'll get to why I call it composing in a little bit, but it's a community-driven effort started by Dell Technologies in partnership with Intel. We have several collaborators, several community members currently at the University of Pisa, Arizona State, and Visius. And then we have contributions coming in from all over the world from different universities, pharmaceutical companies, technology providers, and even cloud service companies. You can go find Omnia online. It's on GitHub. If you go to github.com/dellhpc/Omnia, you'll be able to find all the source code there. And what we're doing with Omnia is we're not really building anything new. We're leveraging best of breed software. So we're looking out in the ecosystem. We're finding the best software for every specific capability we need. And then we're integrating that into the Omnia framework, which is really just a set of Ansible collections and playbooks that help us to automate the deployment and integration of all these components. So whether it's tools for doing accelerator deployment, tools for setting up container runtimes, different schedulers and workload managers and orchestrators, or all of the pieces that go on top of a Kubernetes deployment, for example, like operators and extensions, load balance tools and ingress managers, and even user platforms like Kubeflow, Polyaxon, and Jupyter Hub. We can provide a one-touch deployment for logical clusters within a resource pool. I'll get to what that is in a minute, but we can deploy these logical clusters in different sets of software configurations so that you can set up the type of cluster that the user group needs at the time they need it. And then when you're done, you can actually tear down those resources and reuse them for another purpose. And Omnia does all of this using a 3-step process. So the first thing we do whenever we start deploying software on the Omnia resource pool is we inspect each server in the resource solution. We look at its existing configuration. We look at the operating system that's currently running on it. We take a peek at the PCI bus to determine what network cards are on the PCI bus, what accelerator cards are on the PCI bus. And we collect all of this information so that we can then make intelligent decisions about how to install the right software. So once we've determined, for example, which accelerator cards are in the box, we can pick the installation path for the right accelerator drivers to make sure that the accelerators in the box are enabled and ready to go the second the cluster is brought online. And in addition to the accelerator drivers, we install all the other necessary software packages, including schedulers, container runtimes, and any necessary frameworks, middleware, or Kubernetes extensions. And then once the installation is complete, we then integrate all those pieces together. We set up all the configuration, we do all of the joining of the compute nodes into the manager node, and make sure that when the process is over, you have a completely functional, fully formed and integrated cluster ready to go to accept user jobs. I did mention that Omnia is open source, but on Intel platforms, we do have pro support for Omnia available. So if you want some help from Dell Technologies, dedicated one-on-one support to help with the deployment process, you can buy pro support for Omnia to go along with your open source system deployment. Now, Omnia does things a little differently. Typically, what would happen is if you wanted to set up an HPC cluster, you would set up a management server. You would make sure that the compute image is ready to go, and then you would attach all of your compute hosts to that one management network that's currently being served by your management station. And what that would do is it would provide an operating system as well as all the dependent libraries, scheduling software packages, user level software packages, and the like to every single compute host, and it would build one cluster. And this is a great model if that's what you need. But we've realized from talking to our customers, talking to our partners more and more that the cases we don't want one cluster. What we want to be able to do is lots of different types of workloads on the same pool of resources. And what normally happens is a cluster administrator will set up different queues and try and work around the framework that they've set up in this one cluster. But sometimes that's just not the right way to do it. Sometimes you have to take resources out of a cluster and use them for other purposes. And in a traditional setup, that would require going into the data center, removing the hosts from that management network, and setting up a completely new cluster. Omnia does things differently. Because we separate the cluster deployment and the image provisioning, we can actually build various logical clusters inside this pool of resources, each one of them independently managed, independently scheduled, with independent software deployed on top of it. And so we can build your traditional Slurm clusters for simulation and modeling jobs and MPI work. We can build various different clusters inside this resource pool that have different ML ops platforms like Polyaxon or Kubeflow. We can even build systems that are combined, that are designed to do both artificial intelligence and data analytics, as well as high performance simulation and modeling, all together on the same system, running both Slurm as well as Kubernetes resource managers. And when we discover that resources need to be reallocated to other places, we can change this. We can actually destroy clusters and pull those resources back into the resource pool to be used for something else. We can shrink clusters, we can grow them, and we can create new clusters on demand, as long as we have the resources to do it. And all of this is done through the Omnia control plane. Control plane itself is an Omnia deployment. So it's a self-bootstrapping system. And what you do is you deploy the Omnia control plane on a single server, and it provides a complete environment that handles all of the OS provisioning for every single server in the resource pool. So it'll automatically detect and configure infrastructure either via iDRAC, if you have an iDRAC enterprise or data center license. So if you're running PowerEdge servers with either Intel 2nd generation or Intel 3rd generation processors, Xeon Scalable processors, it will actually look to see if you've purchased an iDRAC enterprise or data center license. And if so, it will use that out-of-band management system to do all of the OS provisioning. Otherwise, it will just fall back on open standards PXE-based provisioning. And so you can mix and match all of your infrastructure inside of an Omnia resource pool. If you happen to have special purpose hardware or white boxes from a particular vendor, you can mix and match all of that infrastructure and make it all feel like part of a seamless environment, even though it's not all exactly from the same vendor. The control plane can then handle all of the deployment for creating on-demand clusters inside the Omnia resource pool, like I mentioned in the previous slide, whether it's Kubernetes clusters, Swarm clusters, or combined clusters that do both at the same time. And then from the control plane, you can even scale those clusters. You can resize those clusters on demand in order to make better use of the Omnia resource pool. Now, software management inside of these clusters is very complicated. So this is the traditional view of what software management looks like on a traditional HPC system. And what we typically see is we have different compilers, different MPI libraries, different math libraries, and then the same application recompiled with all of these different combinations. So in this one picture, we have 3 applications, but each one of them is compiled 6 times in order to get the different math, MPI, and compiler combinations that we want. And this is all managed with modules or some other form of environment management system. And it helps to reduce the complexity to the user, but it still remains extremely complicated for the HPC systems administrator to handle all of this. And it's a very time-consuming process to build all of this software. And so Omnia is taking a different approach. We're taking a container-first approach where we set up the underlying platform, the underlying components with the scheduler and the container runtime, and then you bring the container you need to the system when you need it. So the container would contain the application, the deep learning and machine learning framework, compilers and interpreters like the C compiler, the Fortran compiler, or Python interpreter, your math libraries, your MPI libraries, all of that is contained within the container. And the different technology vendors, like our partners at Intel and AMD and NVIDIA, provide all of these resources already through their own container registries. Intel has one container, NVIDIA has NGC, AMD Infinity Hub. There are even applications for Xilinx FPGAs available through the Xilinx marketplace. And so you can already get all of these heavily optimized containers from the authoritative source, from the hardware vendor, to be sure you're running in the most performant way possible on the hardware that you have. And then you can also get containers from wherever else you need to get them. OpenHPC publishes a set of containers for the new OpenHPC2 environment that provides a very common way of having that familiar OpenHPC experience. You can also get them from Docker Hub or Quay, or even build a local registry and run the local registry for your users inside the data center. Like I said, Omnia is a community-driven effort. We're completely dependent on the community to provide us with suggestions and feedback and ideas and code contributions. And so I encourage everyone to check out Omnia on GitHub. You can go to github.com/delhpc/Omnia. You can star the repo, clone the repo, download the tarball, give it a try, submit a bug report or a feature request, or just let us know that you like it or don't. All the feedback you can give us is going to help us produce a better open community-driven framework going forward. If you're part of the Dell HPC community, you can join the Omnia channel on the Dell HPC Slack. And if you're not part of the Dell HPC community, you should consider joining. Go to dellhpc.org and you can sign up to join the Slack. You can sign up for the weekly community meetings and get great information on what we're doing and what the community as a whole is doing in the HPC space. You can also follow Omnia on Twitter and LinkedIn. Just look for the Omnia HPC hashtag on both Twitter and LinkedIn to get information on new releases, when we're giving talks, and just to have a conversation with us about what you would like to see in the Omnia framework. And if you're using Omnia or you start using Omnia, consider having your organization become a community member and join Dell, Intel, the University of Pisa, Arizona State, and Visius in building the next generation of composable software-defined HPC deployment tools. Now, we have a longer talk that's coming up in the SC21 exhibitor forum. So we're going to actually go over this material as well as show some examples of how to actually deploy, operate, and tear down clusters inside the exhibitor forum talk. You can catch that Thursday at 11 a.m., either online or in room 263. And so just look for Omnia in the SC21 schedule, and you'll find find all the details. With that, we hope you check out Omnia. Keep enjoying everything that's going on this week at SC21. Dell has a lot of great content that they're sharing, even though we're not there in person this year. So check out the Dell Technologies online virtual booth. Go to the Omnia GitHub page and follow Omnia HPC on Twitter and LinkedIn. And with that, I'll stop and we can take some questions.
Good job, Luke.
Thanks, Ed. Just not the same when you can't lure people into the booth from the trade show floor.
Yeah, it's a different world, isn't it?
Yeah, maybe next year.
Yeah. Well, thank you.
Yeah, of course. Hey, Kushbu, how are you doing?
Thank you, Lou. Yeah, it was great to know about it. Yeah, I look forward to getting a repo and then trying my hands on it.
Yeah, give it a try. It's a fun little project.
All right, I guess, Tori, we can close the session, I guess.